let's switch to a different example and consider cones. You may recall the formula for the volume of a cone with a circular base of radius r and height h. Let's turn our cone upside down, putting the point at the origin of the xy plane in profile, and then consider slicing along disks that are parallel to the x-axis. All of these slices are going to be disks of some radius, and so the volume element is going to be pi times x squared dy, where x is the radius of this disk. But we want to integrate with respect to y, since our thickness, our differential element, is dy. So, writing things as we have done so with the apex at the origin of the plane, we see that the equation for the line that determines the profile of the cone is y equals h over r times x. Solving for x as r over h times y, we substitute into the formula for the volume element to obtain pi times quantity r over h y squared dy. And now, to compute the volume, we integrate this volume element as y goes from 0, the bottom, to h, the top. Pulling out the associated constants gives pi r squared over h squared. What's left is the integral of y squared dy, which is, of course, y cubed over 3. Evaluating from 0 to h yields the perhaps familiar formula 1/3 pi r squared h. Now, what happens if, instead of a cone with a circular base, we consider something else? Let's say a square of side length s. Proceeding as before by turning the cone upside down and slicing along lateral planes, we see that the volume element is a thickened square of some side length. What is that side length? If we solve for the line that constrains y in terms of x and solve for x, then we obtain a volume element that is 4x squared dy, namely 4 times quantity s over 2h y squared dy. Integrating that to obtain the volume leads to the integral of s squared over h squared times y squared dy, as y goes from 0 to h. Pulling out the constants, we are left with the integral of y squared dy, yielding y cubed over 3. Evaluating from 0 to h and multiplying by those constants out in front leads to 1/3 s squared h. You may sense a pattern here. In both cases, it was 1/3 the area of the base times the height. Well, it turns out that this is true in general for any cone with a base of area b and height h, no matter what its shape. We can, by turning it upside down and slicing, obtain copies of that base, copies that are rescaled by some factor, so that the volume element is b, the area of the base, times some factor, times the thickness dy. The question is, what is that scaling factor as a function of y? Well, let's say that you go halfway down. At y equals h over 2, what is happening to the area of the slice? The area is not decreased by 1/2. Rather, it is multiplied by a factor of 1/4. That is 1/2 squared, because we're rescaling both directions. Therefore, the appropriate volume element is b times y over h squared dy. And when we integrate that, we see that the constants b and h squared come out in front, and what's left is the integral of y squared dy. Evaluating that from 0 to h yields 1/3 the base times the height. And so we see that the real reason for that 1/3 in the volume of a cone comes from integrating y squared. That's a nice insight to this classical formula. And so we see that the classical volume formulae still hide insights. Now we know why there's a 1/3 in the volume of a cone, and why there's a 4/3 pi in the volume of a ball. In our next lesson, we're going to turn from these simple volume formulae and consider some more complex objects.